Hi all, welcome back to Computer Organization course. We'll get started. Today we will get started with the revision of the second chapter. So before starting the revision, I would like to share that here in the section of your canvas, okay, the last section, you can find the old question papers. It is a document, but it contains question papers of like 4 to 5 years, okay. I have put it in a single document for your ease, okay. Next, we'll start off with the revision. So the first question in the second chapter is explain byte addressability. Okay. So let's discuss like what should be the answer for this question. So go back to canvas. So what I'll do today is like I'll show you the answers which are there in the canvas. Okay. So we have to go to the second chapter and this first one, memory location and address. Click on that. So I would suggest you guys you draw the diagrams which are present here, the basic three diagrams here, and then explain that. Then you explain what is byte addressability. Okay. So I'll tell you guys what to write and all. I'll explain the answer for this one. So in your memory, you can have instructions, numbers, and operands, right? So that your memory is organized in such a way that this group of n bits can be stored or retrieved or in a basic operation. Now the group of n bits we call it as a word, and n is called as the word length. Here you could see, right? So this entire group we call it as one word, and the number of bits we call it as word length. Okay, so this is a typical representation of collection of words. Like this is your first word, this is second word, then it continues, this is the last word. Now as we all know that a word could be of, it could range from 16 to 64 bits. Now this is the representation of 32 bits. That means 4 bytes. Okay. Now these 32 bits or a single word, what it can contain is like either it can contain 2's complement of a number or ASCII 4 ASCII characters. Now these 4 ASCII characters, each of those ASCII characters would occupy 8 bits. Getting it? Now once this is done, what you have to write next is what is byte addressability. Okay, we know that a byte is equal to 1 byte is equal to 8 bits, and your word length would typically range from 16 to 64 bits. Now how do you assign the address for these individual bits in the memory? I'm talking about bits now. A word would be there, okay, and in that word we would have number of bits, right? Now how do you address these bits? So it is impractical, or it is not a good solution to give distinct address or different address to these bits in the memory. Okay, so what is the best solution for this is give the successive address. Like if it starts from 0, then the next successive would be 1, then it would be 2. Like this we have to give the address for these locations, bits or the bytes in the memory. Now this technique is used in the modern computers. Now this technique we call it as byte addressable memory or byte addressability. Say suppose if we have the word length of the machine as 32 bits, then the successive words would be located at 0, 4, 8, like that. So if you take this example, this basic diagram of the memory, okay, say suppose the first word if it starts, okay, this first word if it starts from 0th location, then the second word would start from location 4. That is because we have considered it is of 32 bits. Okay, now these things you have to write for this byte addressability. Next, describe the big endian and little endian addressability. For this question your answer is here. So go back to home, and in the same chapter search for this one, big endian and little endian assignments. Okay, so you have to draw these two diagrams. One is for big endian assignment, another one is little endian assignment. Now these two are the ways for your byte addressability. How can you address the bytes in the word, okay, or in the memory? So in big endian assignment, what will happen is the lower byte addresses, okay, if it starts from 0, then the second word would start from 4, right? Then it would start from 8 likewise. Now the lower byte addresses are used for MSBs, that is most significant bytes. That is, the left side always it represents the lower byte address. If we consider this first word is of 32 bits, that means we have 4 bytes. So each byte it would be represented in a successive manner. So here it is 0, next it would be 1, the next byte would start from 2, and the next one is 3. Now how in the in the big Endian system, how you have to how you have to do assignment is like the MSB, this is called left side it is called as MSB and right side it is called as LSB, least significant byte, and this is most significant byte. In big Endian system you have to use lower byte address for MSB. Remember this. Okay. Now what is little Endian? So it is the opposite of your big Endian system. That means you use lower byte address for LSBs. Okay. So this is the difference between your little Endian and big Endian assignments. Now these two are used in the commercial machines. So in the both cases we have the byte address 0, 4, 8. We have taken these addresses for the successive words in the memory. Okay, to perform any read or write operation. So why we have taken 4? We have assumed that the word length is of 32 bits. Okay. The third question is explain basic memory operation. Okay, for this question, the answer is here. This one, 2.2 memory operations. Just let me read the question again. Sorry. Explain basic memory operation. Yeah. So this is your answer for this question. So in this question, you have to say like what are the basic operations involved. Then you have to explain them. Okay. Now let me explain this one to you. So your memory, it contains both the instructions, that is the programs, and its data or the operands. Now to execute an instruction, what should happen is your processor, it should send the address to the, it should reference to that particular address in the memory, and from that location it has to either fetch the data or it has to take the instruction, and then your processing should start or execution of that instruction will get started. Now there are two basic operations here of the memory. The first one is load and the second one is store. The load operation will be also called as read or fetch, and the store operation will be also called as write. Okay. Now you have to explain these things. What does the load operation do and what does the store operation do? So the load operation, what it does is it transfers a copy of the content of a specific memory location to that of a processor. Whatever the contents are there present in the memory, you have to transfer them or copy them to that of the processor. We should understand here the memory content will not be changed. Now how this load operation would be started. Now to start this load operation, the processor, what it will do, it will send the address of that particular memory location to the MAR. Then from MAR it would point to that location in the memory and a read control signal would be initiated. Now once the time elapses, what will happen? From that particular location which is addressed by MAR, the data would be read or copied and then it would be sent to that of the processor. Now the example of this could be here, this example, load a comma r0. Load is the operation here, a is the memory location, r0 or r0 we call it as a general purpose register which is present in a processor. Now this load a comma r0, what it will do, say suppose we have say suppose your a, it contains the value 5. Okay. Now whenever this operation is performed, the content of a would be transferred to that of r0. Say suppose the content of a is a memory location, remember this one. So the content of a is 5. Now what would happen? The content of this a is copied and then moved to r0. So your r0 will now have the value 5. We should note here that the content of A remains unchanged. Next, the store operation. What will happen in a store operation? Now, the store operation, it transfers the item of information. Okay, it transfers an item from your processor to the specific memory location. Now, how it is done? The processor, it again sends the address of the location to the memory via MAR. Then a write signal would be initiated into it. Initiated, that means the whatever the value is calculated, or you want to transfer something from processor to the memory location, we use store operation. We have to understand here. Now this store operation, it destroys the contents of the former contents of the memory location. If we take example here, suppose this one, store r0 comma a. Say suppose r0 has a value 23. Okay, now you have to move this value 23 to that of memory location a. Now what will happen? Say suppose your a was previously containing the value 50. Now once this instruction is executed, what will happen is this 50, which was the former content of memory location A, is destroyed, and the new content, which is the R0 content, would be placed in the memory location A. Understood? So if possible, mention these two examples as well for this question. Okay. The next question is explain straight line sequencing. Okay. So the answer is here. Go back to the second chapter. Straight line sequencing. Okay. 2.3.4 instruction execution and straight line sequencing. So this is your answer for that. Give me a minute, let this load. Yeah, you have to draw this diagram and you have to explain what does it do. Getting it? And explain this one. Okay, so let me explain this for you. So basically we have a diagram wherein you have a code snippet for the instruction C is equal to A plus B. That means the contents of A, memory location A, which is represented here, and the content of memory location B, these two things to have to be added, and the answer, the result, have to be stored in the location C, in the memory location C. Okay, now we will assume that we have a 32-bit word length. That means we have the byte would be presented successive 4 bytes. Okay, so if it starts at byte I, then the next word would start at byte 4, because we have assumed that it is one word is of 32 bits or 4 bytes long. Okay, now we will understand this execution, what will happen. So first what happens is your program counter will point to the instruction I. This is the first instruction. So your program counter will point to this. That means your PC, that is the program counter, it will hold the address I. Now this I should be transferred to that of MAR. Okay. Now what will happen is once you transfer the address to the MAR, what will happen? That particular location's instruction would be fetched and it is executed. Now in the meanwhile, what will happen when the instruction execution is going on? Your PC would be pointing to the next instruction, that is I plus 4. Now when this second instruction is getting executed, what will happen? Your third instruction, your PC will point to the next instruction. Now how is your PC incrementing? It is incrementing one by one, right? First it is incrementing successful, it is incrementing successively. So what will happen is the executing of this particular given instruction is a two-phase procedure. In the first phase, what will happen? That is called as instruction fetch phase. Your instruction is fetched from that particular memory location, which is pointed to by your PC, then your instruction is read and it will be moved to the instruction register, that is IR. Now the second phase we call it as instruction execution. Now in this phase what will happen? The instruction which is already present in the instruction register, it is examined to determine which operation to be performed. Either it is add, subtract, whatever it is. In our case it is add. So the operation will be then performed by your processor. In general we will say that it would be done by processor, but actually it would be done by your ALU. Now your addition operation, or execution of that particular instruction which is in the IR, so it involves fetching of the operands again from the memory, right? So what will happen in this case is, whenever this type of instruction is present, then another read cycle would be initiated, so that your operands will be again fetched from the memory. Then you will perform the arithmetic or logic operation. Then what will do, you give back the result or store the result in the memory. Now at some point during this two phase execution, like the instruction fetch and instruction execution, what will happen, your PC will point to the next instruction. Okay, so here straight line sequencing is nothing but your processor control circuits use the information in the PC, that is program counter, to fetch and execute the instruction one at a time in the order of increasing address. Remember, in the order of increasing address. Now this is called as straight line sequencing. Hope you are clear with it. Okay. Next, write a note on conditional codes. Okay. Let me show you where the answer is. Go back to second chapter and topic 2.3.6, that is condition codes. So you have to write this thing. What is a condition code? Then the example of this one, example for the condition codes, and explain these things. Let me explain this for you. Consider an example or the instruction where which says branch less than 0 loop. We had seen this one, right? It is a conditional branch. So in this case, your processor, it will keep track of the information about the results of that operation by using a conditional instruction, branch instruction. Now how this is accomplished is by recording the required information in the individual bits. We call that individual bits as a condition code or condition code flags. Now these flags, condition code flags, are usually grouped together in a special purpose register, and we call that register as status register or your condition code. Okay, so you'll have a register which will say, suppose it has 8 bits. Okay, now each bit in that status register would represent some condition code. Now these condition codes or the bits, either it would be set to 1 or it would be cleared to 0 depending upon the outcome of the operation they are performing. Now the examples are N flag, that is negative, Z flag, that is 0, V overflow, then C is carry. Now your N and Z flags, they will indicate whether the results of the arithmetic and logical operation is either negative or it is 0. Now these N and Z flags, they are affected by the instructions such as move, load or store. The V flag, it indicates whether any overflow has occurred. If overflow has occurred, then it would be set to 1, otherwise it would be cleared to 0. Then the last is C flag, that is carry. It is set to 1 if a carry occurs from the MSB or the most significant bit position during an arithmetic operation. Now, this flags makes it possible to perform arithmetic operations on the operands that are longer than a word length of a processor. If there is no carry, then it would be set to 0. Okay, getting it? The next question is describe register and absolute addressing mode. So the answer is Go back to the second chapter 2.4.1. Okay, this one. Here is the answer. Okay. The implementation of variables and constants. In this topic, you have the register mode and absolute mode. Okay. Now we will discuss about what are these modes. Like first one is register mode. Now in this register mode, what will happen is the operands will be the contents of a processor register. The name of the register is given in the instruction. For example, is given in the instruction. For example, move R1, R2. These R1 and R2 are your processor registers. So this is an example of your register mode. Register mode. Now what will happen here is, okay, this should be R1, R2. Yeah. So this move R1, R2. It states that the contents of the register R1 should be moved to the R2. Okay. The next one is absolute mode. So here the operand is the memory location. The address of the memory location is given explicitly in the instruction. This is also called as direct mode. Absolute mode is also called as direct mode. The example of this is move LOC, R2. Now here LOC is your memory location. Now this instruction, it says that the content of the memory location should be moved to that of your processor register R2. Getting it? Now, your absolute mode, it can also represent the global variables in a program. The declaration such as int or integer a comma b, what does it specify is, so you have to allocate the variables in the memory location a and b of type integer. You have to allocate these many bytes to the location a and b. Okay. So this is your register mode and absolute mode. You have to write till here. Okay, integer a comma b till here you have to write it. So hope you are clear with the answer for this one. Explain register mode and absolute mode. So the next question is write a note on relative addressing. That's it for today. We'll conclude our session. Thank you.